Good morning, everyone. Thank you very much for being here at this time. And thanks to the other committee for inviting us to share our thoughts with you today. How am I supposed to? Yeah, I think. Okay. Before we start running through our presentation, I would like to ask you a couple of questions. Have you ever experienced challenges in discussing books' mechanical issues with other colleagues or young learners? When repairing a large format or a heavy book, for example, how do you judge whether the materials and the techniques you choose will be adequate to address its specific conservation problems? Well, the attempt to find an answer to these questions is where it all began. Does it move by itself? Okay. In 2019, we started a project on large format volumes for Paola's MA conservation thesis, which included a comparison between different conservation techniques. Yes, because it's moving by itself. I'm a bit scared. Okay. A comparison between different conservation techniques and an assessment of their effectiveness on the book mechanic. In order to make the comparison as objective as possible, we wanted to measure the functioning of the structural elements involved, trying to turn concepts and observations into numbers. Is this possible? And in case it is possible, how can we use those numbers in a meaningful way for conservation purposes? So we teamed up with experts from the Politecnico University in Milan, Professor Alfredo Cicada and Professor Emanuele Zappa, based at the Department of Mechanical Engineering, Mechanical and Thermal Measurement Division. They joined the project with great enthusiasm and an inspiring, open-minded approach. As a first step, we looked for similar studies in our field. We were able to find very few resources published, probably because of the subject's vastity and complexity. The body of the studies we found deals mainly with the description of the joints and spines functioning mechanisms in standard book structures. This choice was made to streamline the analysis of the physical process by simplifying the scenario of the multiple bookbinding styles existing. However, movements do change according to several factors, such as the size and weight, for example, and specific types of books eventually behave differently from the standard cases studied. Large format volumes, for instance, may suffer from amplified and diversified strain, which need to be specifically considered. We found no mention in literature regarding the use of scientific tools to quantify stress or to verify the efficiency of structural elements, except for Jan Sirma's study. He evaluated the performance of book joints by means of a folding resistance test. Despite the great work done by scholars to improve our understanding of the book's mechanics, the treatment choice remains a difficult judgment call, based on the professional experience, sensitivity, and skill set of the individual conservator. With all this in mind, we decided to go for a different route, trying to set up a scientific method to analyze the book movement. In fact, we wanted to measure and quantify the forces involved to improve our true understanding of the physical interactions between the binding elements. Instead of simplifying the book action to make it applicable to a standardized prototype, we wanted to reconstruct its complexity by analyzing the several stressings affecting simultaneously the binding. Therefore, we broke down the structure and action of the bound volume to identify the individual forces involved. The effects of the strain are generally multiple and can be diversified depending on the area considered. Quantifying the intensity of the forces in specific areas could tell us how much that individual movement influences the general action and vice versa. Introducing a successful scientific method could support and make tangible the visual observation and experience we have, adding complexity to our knowledge in the attempt to achieve more objective statements. So we set the aims of the investigation that can be summarized as follows. We intended to gather a science-based understanding of book mechanics, identify what forces are involved in the functioning of the book, including different binding styles, the size or the weight of the volume, find a way to measure the forces involved in the functioning of the book. The outcomes of such a work could potentially support and inform our conservation practice, making possible to assess whether a treatment is appropriate to sustain a specific structural failure and what materials or techniques can be used to overcome combined mechanical problems in book. We started by observing the condition of several large format volumes. We listed the type of damage specifically related to structural failures, which occurred either because of a poor original construction technique or because of a particular stress the book suffered from. This little survey allowed us to draw trends of preferential damage and to highlight joint responsibilities in degradation patterns. Next, we tried to identify and analyze the forces acting on the book, both when this stands on a shelf and when this is handled lying on a flat surface. Bearing in mind that the severity of the damage determined by a force is also related to the time of exposure to it, we deemed crucial to consider what is the real life of a book, whether it is indeed repeatedly subject to handling or not, whether it sits on a shelf vertically or it lies down flat. By identifying the types of forces, it was possible to decide on the measuring methodology and the characteristics of the sample to be tested. Let's now dive in a little deeper into the technicalities of the experimental part of the project. Paola.
The collaboration with the Professor Cigada and the Professor Zappa made possible to set up a method to monitor and measure the forces involved in the opening of the book. The work presented here explores the feasibility, the limitation, and the possible future developments of such method. The data collected allowed the acquisition of some original information on book mechanics. The method we were looking for was, of course, aimed at measuring forces in a meaningful and reproducible way. We started by looking at the forces acting at the hinge of the front board of a book. To achieve this, the opening movement was simplified and sketched in such a way that the system could be compared to a second-class lever. A second-class lever is a simple machine composed by a rigid beam that can rotate freely around a fixed point called fulcrum. The load or weight is located between the fulcrum and the effort or force. In our case, this corresponds to the weight of the board to be lifted. The effort is applied on one side of the resistance or load, and the fulcrum is located on the other side. The data collection system was selected by our engineer partners so that this will be simple to operate by a person with no engineering background, precise and repeatable despite including a main operating element, contained in cost and easy to set up. The system was made by several elements: a strain-gauge load cell capable of converting a force, such as tension, compression, or pressure, into an electrical signal that can be measured and standardized. It's a force transducer, highly accurate, versatile, and cost-effective. Structurally, a load cell has a metal body to which strain gauges have been secured. The body is usually made of aluminum, alloy steel, or stainless steel, which make it very sturdy, but also minimally elastic. The deformation caused by the force acting on the cell can be measured. The cell used for our experiment has a sampling sensitivity of 0.01 Newton. A non-elastic wire connects the strain gauge cell to the book board. The second element is a data acquisition system able to convert analog waveforms, the change in electrical resistance, into digital value for being processed by a computer. The third element is an high-resolution digital camera set to acquire 2 frames per second, which allowed for a representative number of images without exceeding the storage space used. The fourth element is a software called LabVIEW 2019, which allowed the calibration of the strain gauge cell as well as the synchronization in data and image acquisition. It made possible to transform the variation in value in electrical resistance into force values to be measured in Newton. The data acquired from the cell are difficult to read as they report the variation over time, but have no connection with the opening angle of the volume. The data require interpretation following the collection. The last element is a vision assistant tool, able to calculate the opening angle of the volume by using an edge detection algorithm. Its use made possible the identification of the force trend in relation to the opening angle. To run a preliminary test, the strain gauge cell was connected by the wire to an ordinary book prototype already available, so that the front bore could be lifted or moved. The book was placed on a raised flat surface in front of the camera, set up to record the book's movement throughout each single measurement. Measurements were first taken lifting the front board only. Subsequent tests were made to include data related to the simultaneous lifting of boards and text leaves, so that the movement of the spine could also be monitored during the opening. However, some shifting issues made the measurement inaccurate, and it was decided to leave this aspect temporarily aside. The first tests were carried out taking into consideration different points of application of forces. To assimilate the system to a lever, certain conditions had to be guaranteed. One of the fundamental requirements was the positioning of the wire, that needed to be perpendicular to the surface onto which the force was applied. The force was maintained perpendicular to the board only when the wire was attached to the foredge of the book. For the first tests, according to the expectation, we could notice that the force necessary to lift the board increased proportionally to the reduction of the distance from the hinge. Given the weight of the board, the system also allowed to calculate what is the proportion between the weight and the force required to open the volume. Additionally, it's possible to find out how much resistance comes from the board when the book is resting on a flat surface. The weight of the board can be used to calculate the forces acting on the fulcrum. The results obtained in this phase confirmed that the experiment was reproducible because, under the same condition, there were no significant differences in data collected. No major changes was observed, neither when the operator changed. In fact, the maximum difference recorded between the individual tests was only 0.08 Newton. Once the system proved to be useful for our aim, it was time to select the samples and verify the research hypothesis. To appreciate variation in measuring different characteristics of books, we decided to create two prototypes. They both had the same binding structure, the same size and composition, but their orientation was different. So one book would extend horizontally, landscape format, while the other one would extend vertically, portrait format. The production of these two models allowed us to perform tests at different stages of their binding construction, so that the following elements could be observed. The behavior of the hinge at different steps of binding construction, the contribution of different binding components to the movement of the hinges, the variation in measurement due to the different orientation. The analysis of the portrait format did not highlight greater variation across the binding construction process, except for the last step, which included the application of leather back. There is no clear pattern or linearity in the evaluation of the movement other than a reduction in the initial forces values and a shift in the maximum values around and above 50 degrees opening angle. This corresponds to the application of the leather back, which, by compressing, determines greater resistance. Comparing the data with the ones obtained in the ordinary prototype book used to perform the initial tests, it appears clear how the weight of the board influenced the necessary forces value and their distribution along the surface. The landscape volume, on the contrary, show considerable differences in the distribution of the stress during the opening, before and after the application of leather spine. Before the leather was applied, the force value increased very quickly up to 20 degrees opening angle to get stable and tend to zero around 90 degrees opening angle. After the application of the leather back, a greater distribution of force is observed throughout the entire arc, with the maximum value being reached above 40 degrees opening angle. In the image on the screen, we can appreciate even better the difference determined by the presence of the leather back, which being compressed determines a greater resistance. The comparison between the data collected when both bindings were completed shows how the increased dimension of the hinge determines greater or lower distribution of the forces necessary to lift the board. The data recorded in relation to the weight of the board are inversely proportional to the distance of the point of application of the force from the hinge. In vertical volume, the force applied at the foredge is equivalent to 55% of the weight of the board, while in the horizontal volume, the force applied on the foredge is equivalent to 44% weight of the board. The variation is due to the increase of length of the force arm applied.
To conclude, this first experiment showed some interesting results, highlighting, for example, how the force applied to the board is forage distributed during the opening of the volume. It also showed how the format of the book and the weight of the board determine considerable variations in the hinge movement. The possibility to compare the book mechanics to a simple machine, and particularly a second-class lever, makes somehow possible to turn empirical observation into something that can be measured. The process is far from being simple and has a number of limits that need to be overcome. However, it does show an interesting potential to enrich the knowledge we already have and to better inform our conservation practice. Much work is yet to be done. The project is just born and will need time, resources, and competence to blossom. We would welcome any feedback from you, so please come and talk to us. Thank you very much for listening.
Thank you, Sara. Any questions from the public? Yes, there's one at the back.
Hello, thank you for the very interesting presentation. What type of leather did you use for the experiments? And have you considered also altering the cover material with maybe book cloth or background, just to compare?
Sure, no, absolutely. Well, the type of leather we use to start testing the method, because what we actually started doing is trying to find the method, because it's not so straightforward at all. We just use an ordinary vegetable tanned. I think it was calf leather. But really, we weren't, at this step, we weren't really bothered by the type of materials we were using, because we were just trying to find whether there was a method we could use and how successful this could be. There are limits in this method, but something has come out, so it needs a lot of work on it. And in the future, we certainly think that we have to test a lot of different materials, a lot of different constructions, of course. So this is really just the very start of it. Thanks for the question.
Any more questions or comments? Well, I'll ask one.
Yes, thank you.
So you tested on the mock-up book.
Yep.
And also you took the pictures of how the book opened. Could that eventually be applied to like a book from the collection, and then using the model and AI to take the forces out of just the way in which the object moves?
Yeah, no, absolutely. The mock-up is really, again, just the start, and maybe it didn't come out from the slides, but what we did is measure the forces throughout the building up of the binding. So we'd know just with the sewing, with spine lining, and with end bands, and then with the cover. Yes, the end of the project would be to actually test it on a selection of standard bindings that we have to understand really how things change in real life, and what are the different elements that we need to consider when thinking of repairing a joint. It's not just a joint, there are lots of elements, and very often forces do counteract one to the other. So we need to understand how that happens and what is more important in that specific balance of the kind of book.